We want to bring the rapid, utility-driven design of the DaisyUI system directly into a native Android application built with B4X. This diagram illustrates an architectural problem. DaisyUI is built for the web, relying on cascading style sheets and the document object model. B4A operates in a separate domain, using native Android XML. There is no CSS rendering engine here. To see what happens when we ask a standard large language model to bridge this gap, we give Claude a zero-shot prompt. Build a DaisyUI dashboard in B4X for Android. The result is an immediate compilation failure. Claude injects standard web code into the native IDE. The compiler throws errors, unable to parse div tags. This failure happens because of how LLMs process requests. They generate responses based on statistical proximity within their training data. In those massive datasets, the term DaisyUI is tightly bound to HTML. The model perfectly understands the visual layout of a dashboard, but it lacks the necessary B4X syntax matrix to construct it outside of a web browser. Requesting an AI to cross from a web domain to a native domain without providing a rigid translation map guarantees uncompilable hallucinations. The model needs an external set of instructions to override its default behavior. Developer Mashiane built the B4XDaisyUIKit skills repository to solve this exact problem. This repository serves as a configuration set for the AI workspace. Rather than compiling it into your Android application as a dependency, you integrate it into the AI's environment. It provides a contextual bridge, a collection of strict rules written for the intelligence to read, rather than the compiler. We are analyzing version 0.90, which includes specific parameters designed to guide AI code creation. The repository intercepts the LLM's standard processing path, overriding its statistical assumption that DaisyUI requires web technologies. By injecting these deterministic rules into the prompt pipeline, developers can force the AI to abandon web hallucinations and generate strictly native code. This file tree shows the override mechanism, sitting at the root of the repository in a directory named .claude-plugin. When you open the project, the Claude desktop application automatically scans this hidden directory and ingests the data into its context window. The critical instructions for generating the interface are located in the skills/B4X-DaisyUIKit subdirectory. Inside, JSON configuration files and raw text prompts establish the translation protocols. This technique is known as system prompt injection. These files operate as an invisible filter. They append strict operational constraints to the model's memory before the user types a single command. During discussions about user interfaces, the injection restricts the model's output vocabulary exclusively to valid B4X layout declarations. This architecture modifies the LLM's initial state. It takes a web-biased generalist and forces it into the role of a constrained B4X DaisyUI specialist. This technical view demonstrates the translation matrix in real time as we submit a new prompt. Generate a profile card using the B4X DaisyUIKit skill. The user intent requires a primary background color, denoted in the DaisyUI system as BJ primary. The skill intercepts this utility class and maps it through the matrix, outputting the exact B4X method, color equals XUI.colorRGB. The design also requires rounded corners, represented by the class roundedLG. The matrix intercepts this and writes setCornerRadius directly into the native IDE. The translation mapping extends to the structural physics of the layout as well. DaisyUI's grid and flexbox utility classes, like Flex and Gap4, are converted into complex B4X anchoring and layout constraint methods. Padding and margin utilities, such as P4 or M2, are translated into precise device-independent pixel measurements. The skill files force the LLM to bypass its neural network probability algorithms and reference a hard-coded dictionary. Dictating a granular mathematical translation at the class level ensures the AI generates pure native views that perfectly emulate the requested web design. When finally executed, these highly localized and translated code snippets rapidly assemble themselves into a complex, polished mobile interface. Unlike the zero-shot attempt, this output complies perfectly within the B4A Visual Designer without a single syntax error. The traditional method of achieving this aesthetic involves wrapping DaisyUI web code inside an Android web view, which consumes high amounts of system resources. This pure native approach yields significantly faster render times, strictly managed memory allocation, and smooth scrolling performance. Bridging the context gap merges the rapid design iteration of a web framework with the uncompromising performance of native Android code. Utilizing localized AI skill injection provides developers with modern web design ergonomics directly on mobile platforms. Mastering this .claude-plugin workflow eliminates the requirement to learn heavy hybrid frameworks like React Native or Ionic just to access modern UI systems. To integrate this system, developers must navigate to GitHub and fork the B4XDaisyUIKit-skills repository. Downloading the code is only the first step. Activating the translation matrix requires actively integrating the .claude-plugin directory into your local workspace environment. Providing the AI with these specific architectural rules allows web-based design systems to become functional native realities within the B4X ecosystem.